Yes. Good evening, everybody. This is SuspectSky. So finally got some new data on the latest fast radio burst, and it's pretty interesting. For you new followers, I'm just going to do an extremely brief overview of the whole phenomenon, and I'm going to include a bunch of links to my prior videos on the subject. So my old followers, you'll know that I've been watching this phenomenon for about 6 or 7 years now, keeping a real close eye on it, and it maintains its mystery. It keeps getting weirder. So new people, this is an example of a fast radio burst. It's a highly energetic 1 to 2 millisecond burst of radio energy that radio space telescopes detect, and there's no general consensus as to what causes them. And this is unusual because usually over time we can determine the sources of these objects, and we've been detecting these for about 10 or 11 years now. So it's a really fascinating phenomenon, and scientists joke that there are as many natural origin theories as there are fast radio bursts that have been detected. Everything ranging from massive collisions to gamma ray bursts, and they all have their flaws that other scientists point out. And the frustration that the scientific community has had with explaining these has led even some of the top scientists from Harvard to theorize that fast radio bursts might come from alien space travel. And this concept is that they would use giant reflecting disks to harness the power of the sun and turn it into radio energy to burst solar sail vessels and solar sail probes around their local region. So it's exciting that even Harvard scientists are considering an artificial signal as being a possibility. What really intrigued me initially was the first 10 fast radio bursts were all equal multiples of the number, this strange number 187.5. 1, 2, 2 multiples, 3 multiple, 4 multiple. So this is a measurement of dispersion measure, which is used to estimate the distance of the origin source from Earth. And oddly, they were all equally spaced distance from Earth. And this really got a lot of people thinking that these might be artificial. No known natural process could explain this in a generally accepted homogeneous universe whereby pulsars and other natural objects, they're not going to be spaced equally apart from each other as in our understanding of the universe. So finally, the data of the most recent fast radio burst has been released. And most importantly to us is the measurement of dispersion measure. And it gets interesting. So here is, well, actually, maybe I'll show you this slide. So here's a slide from my Pittsburgh conference in 2011. I was keeping track of this. So this Michael Hipke of the Institute of Data Analysis in Germany, he came up with this strange observation, and even he thought that this was highly indicative of unnaturalness. It was concentrated in the median, which is also very strange. And I'll see if I can dig up a link to the conference video itself. But so they finally released the data on this most recent fast radio burst, and I went back to my old Excel sheet here. So this is my sort of thought pad. So every time something with fast radio burst happens, I just start playing around in this Excel worksheet. You can see I have a bunch of graphs here, multiples in order of receipt, and how it's kind of an interesting slope. It's kind of straight. DM values in order of discovery. And keep in mind that a lot of this stuff is old news, old observations and old analysis that I've done. And this is one thing I found interesting, and I don't think we've answered this question yet, but I thought it was interesting that there were 8, and then there was a double pulse, and then now I guess we'll see if there's a correlation to 8 here going on. So I'm still waiting to see that. But I was able to take all the data, so the old and the new data, and put it all together in this chart. So here are the 23 FRBs to date listed here, and their dispersion measures. They're multiple to 187.5. So this 746, is a multiple of 3.9786 yada to 187.5. And then I did some rounding here just to make it more illustrative, to show you how bizarrely close these all are to a multiple of the number 187.5. Many of them are even exact multiples. Then I had the observation that 2.5, 1.5, and then now the most recent multiple is 3.25. these are fractional multiples. So they still kind of fit the model to me. There are a couple outliers, and that is the ones in the yellow. These are the ones that don't really match the model. So I've highlighted those in yellow, 4.6, 4.2. And then these blue ones, I noticed they're starting to keep track of plus or minus now. So this dispersion measure is known to a plus or minus of 11. This one's known to a plus or minus of 7. This one to 3. And I thought it was interesting that maybe then this is a multiple, and then maybe this is a fractional multiple, because we don't really know this dispersion measure that well. So, you know, if we did, these two might be they might all still be on the model here. So I thought that was kind of interesting. And then that got me thinking too, why didn't they keep track of that information before these ones, plus or minus amounts? Because maybe we could have a better understanding, and maybe these ones that are sort of off the 187.5 theory, maybe they would now be in line with the 187.5 theory. So I don't know. You know, it's interesting. This unnamed repeating burst. So this is 10 repeating bursts, all at a multiple of the number 3. So I've left this out of my analysis because it's a weird one, and to have 10 bursts listed all as a multiple of 3 would skew the data, so I'm trying to be conservative here. But just imagine if there were 10 more, all with the 187.5 multiple of value of 3. So we're being conservative here. But anyway, I have some other interesting data. Here's the average dispersion measure is 772. The average multiple is 4.1. Yeah, so this is just kind of my running thought pad here. But so then what I did is I took the dispersion measure and I took its decimal multiple of 187.5 to, you know, a factor of whatever that is, 6 or 7, 8, and I put all of that into a notepad here. So I'm going to copy that so you can see here 746 3.97, 746 3.97, and I put all that information into a correlation coefficient calculator. And lo and behold, correlation of 1 with a sample size of 24. Arguably, we have a sample size of, what is that, 34? So that is important, because once you get over a sample size of 30, then things become statistically significant, and the correlation has a coefficient of 1 with 24 and 34 if you count the repeating one. So this still remains a really interesting mystery. You know, why are all these things correlated to the number 187.5? I then took a linear regression. The slope of this is 1. You know, it's really fascinating. You know, I don't really know what to make of it, but it seems like the 187.5 pattern might still be holding up. So if anybody else has any thoughts on this, and actually, I'd be happy to share my Excel thought pad. If anybody knows how to do that, if I can put it in the comments or the description of the YouTube video, just let me know, because it'd be interesting if you guys wanted to play around with these numbers and just kind of see where I've been going over the last couple years. I think that'd be cool. But anyway, so back in 2011, I came up with an idea of what 187 might be, 187.5 might be. And it actually turns out to be the lowest macro state of entropy for 2 Einstein solids. And what's important about that is macro states and entropy and thermodynamic models. I mean, a macro state, the 187.5 means it's the least likely to occur naturally. So that, to me, kind of thought maybe this could be a message, that here we're sending you out a number with our system of beacons out there, that this pattern you're picking up, this thermodynamic pattern, is the least likely to occur naturally. So maybe you should pay attention, is kind of what I thought. And this concept is not lost on humanity either. So humanity has this concept that we should look for life on a frequency of 1420 megahertz, which is the frequency at which hydrogen resonates. So our idea is that there's so many frequencies out there, we need to kind of guesstimate which ones to look at. let's look at 1420, which is the frequency at which the most fundamental element resonates at. It might be a good place to look. Well, extraterrestrial civilizations might be employing a similar methodology in that if we're going to let people know that we're around, using beacons, or maybe they're embedding messages into things they use every day, such as asteroid collision radars. So this might be a neat way to do that, to put in math that, perhaps entropy is more fundamental to them than hydrogen is to us. And maybe we'll pattern these things around 187.5 by equally spacing these beacons. So it's an interesting thought. Harvard scientists are looking at it as perhaps a propulsion technology whereby you're using these things such as transportation hubs like train stations. You're bouncing from equally spaced stations as you move along on your solar sailed vehicles. So the phenomenon continues to be really interesting. We're definitely going to be keeping track of it. And so thank you for your time.